So today we're going to talk about polarization. Before we do jump in, I want to do like a caveat of sort. As weird as interference is, like we just talked about, double slit experiment, how light is traveling through both slits at the same time, and you can actually have hundreds of slits or thousands of slits with a diffraction grating, for example, where you have millions of slits, and a photon is literally going through each slit at the same time. You can turn that into crazy interferometers where you can either measure gravitational waves from black holes spinning around each other millions of light years away, or use it to test whether or not a bomb's going to explode without actually exploding it, right? Interference is crazy. Polarization is, if anything, even weirder. In all of the weird stuff of quantum mechanics occurs within polarization, and we have no perfect explanation for it. So that being said, the first thing we're going to do in this video is we're going to talk about the classical explanation of polarization. And then we're going to talk about what I would call like a newer, more complete explanation of polarization, but it's less intuitive. So I don't know, neither one I like, but we're going to do it and it's going to be great. All right, so like I said, polarization is tricky. You can think of light as an electric and a magnetic wave. In fact, it is. We know it's called electromagnetic waves, right? If we focus just on the electric part, classically we can break the electrical component of the light. Like let's say it's the red here, where it goes up and down and up and down and up and down. We can break that into two parts. So let's say it actually travels not in just the y plane here. Break it down to the x and y plane, right? Where the xy plane is perpendicular to the direction of travel. We could have a wave you could imagine traveling kind of like at a 45-degree angle, right? Or something like that, where it is moving like this in between the x and the y axis. So we can, if we just look at the electric field component, we can describe the electric field component as an x component, which is a function of z and t, and a y component, which is a function of z and t. And each one of these things, if we want to be a little bit more, make this math a little bit simpler, they're actually related by, we can give each one of these a magnitude, call it E naught x I hat plus E naught y j hat times the cosine of kz minus omega t, where omega t is the phase and kz is the direction. So we're always assuming that the ray is traveling in the z direction. It doesn't matter which way it's actually traveling, that is the z direction for this. And what this says, right, is that the x and y magnitudes of our electric field are going to fluctuate like a sine wave, cosine wave, whatever. So what's interesting about polarization is that it's a lot like coherence. Every photon is polarized. So remember how we talked about the double slit experiment works, even if you send a single photon at a time. Polarization works the same way. Every phenomenon that works with polarization has to work with a single photon at a single time. And a single photon is perfectly polarized, but you have to work to make all photons have the same polarization, right? You have to work hard to do that. So when we say something is linearly polarized, a linearly polarized beam means all of the photons have it's a beam in which all of the photons all of the photons' electric fields are oscillating in the same direction. Okay, so you can imagine if one photon's electric field is oscillating up and down, magnetic field obviously will be oscillating left and right, then all of the photons for a linearly polarized beam would also be oscillating vertically. Okay, and the angle, like we said, of the oscillation is given by the relative strength of the two components, and that's really just an arbitrary measurement or arbitrary description, right? Really, the electric field can oscillate in any direction. We've just chosen an x and a y, and we're going to break that down into two components, like we do with forces, like we do with everything, right? So we would say that our electric field maybe is going like this, and there's some angle theta, and we have some ex and some ey, and theta is equal to the tangent inverse of ey over ex. That's terribly drawn, terrible E, right? So that would tell us the angle of the polarization. Again, this is just like a applying a coordinate system to a phenomenon. Like you can split forces into X, Y, and Z. There's only one force, but we can split it into different components. That's exactly what we're doing here. A linearly polarized beam has all of the electric fields oscillate in the same direction, and we can describe the angle that the direction is relative to whatever direction we want to by breaking it into its components and then finding the angle. So this is relatively simple, right? It seems pretty straightforward, except for the fact that this is not a complete description. We can also get circularly polarized light and elliptically. Elliptically polarized light. So for a moment, let's assume that we can break the components for the electric wave into its x. This is, by the way, this is where the classical description of polarization breaks down. Let's assume we can break down the polarization into its x and y components, ex and ey. Right now, we're assuming they have the same phase. So if we look at our mathematical description of these waves, both the x and the y component are multiplied by the same cosine, which means they have the same phase, right? But what if we made the phase different for these two? Well, turns out, go to the next page, we had a little too much space there at the bottom, we can describe this where we allow the phase to vary. So we say that E, our electric field, is equal to I hat times E naught x cosine of kz minus omega t. That looks just like above, but what we're going to do is we're going to vary our J component, J hat E naught y times kz minus omega t plus epsilon, where epsilon is a phase lag. Phase lag between the two components, right? So what we can, like I said, normally if the two are in the same phase, then the magnitude of the electric field is always pointing in the same component. But if we produce a phase lag, so we're going to draw this in 2D first, right? If we produce a phase lag, let's draw the magnitude of these two things first. So we're going to draw an EX. I'll try to do a sine wave. That's not the best, but and then we're going to do an EY. So this is our EX. Now we're going to draw an EY. We're going to put it out of sync by pi over 2, right? So when this is its maximum, this is going to have 0. So it's going to come up where this is 0. This is going to have its maximum, come down. Oops. Come down like this. It keeps going, right? So these two things are, and this is EY. So the Y component of the electric field then would be lagging the X component of the electric field by pi over 2, right? The result is that the electric field actually direction appears to spiral around. So if we draw the location of the maximum electric field, what happens, and this is gonna be rough, so stick with me here. I'm gonna try to draw it. Okay, that was not terrible. So what happens is the location of the maximum electric field appears to spiral in space, right? So as it moves forward, that location starts at like Y, let's say, moves down to X, then goes down to negative Y, and then comes back around. Oh shoot, I didn't draw this very well. It's hard to draw this in 3 dimensions. Right? So the direction appears to spiral around, like I said. Great, that's circularly polarized light. When EX and EY are offset by pi over 2, and then we have a uh, equal magnitude. We can also make the X and Y components not equal to each other. And the end result is we can get, for example, circularly polarized light, or like this. In that case, um, EY is equal to EX, and epsilon, our phase lag, is equal to pi over 2. We can also have elliptically polarized light like this. In that case, we have EY is greater than EX, and our phase lag is equal to pi over 4. Actually, that's wrong. That's pi over 2 still. And then finally, we can have, elliptically polarized light in the other direction, which would be um, something like this, right? But in that case, it's just the opposite of the green one. EY is less than EX, and epsilon is equal to pi over 2. Okay, so this is great. So any beam of light, in theory, we can describe it with um, three descriptors, right? The magnitude of the Y component of the electric field, the magnitude of the X component of the electric field, and the phase lag. And if we know those 3 things, we can describe the polarization, which is awesome. And in fact, um, this description is very convenient mathematically and conceptually, but it's not what's really going on. And we can tell this because remember what we said before when I said that polarization is just like interference. With interference, a single photon can go through multiple slits at the same time, right? Interference has to work with a single photon. It cannot rely on there being multiple photons. But here we've said that a single wave has 2 components to its electric field wave. And those 2 components, X and Y, can have different phase lag. And that makes 0 sense, right? A single wave is going to have a single phase. That's just how it is. And so by introducing this phase lag, what we've done is we've added this kind of kludge, which is not physically realistic, right? Um, when we say that, we say one component of the electric field lags, um, do we have a second photon, which we know has to be false, right? Um, this cannot be true, so this description cannot be true, right? But it works really, really well. Uh, Another case where this description breaks down is when we talk about methods of polarization. So if we want to polarize light, for example, the sunglasses you have, if you have polarized sunglasses, polarization describes that the theory of polarization says that those sunglasses absorb one direction of electric field energy and leave the other direction undisturbed. And so the result is they absorb at least 50% of the light. So, like, let's say they're vertically polarized, they would absorb the horizontal polarization and leave the vertical to pass through, right? And you can look this up on YouTube or Google or all kinds of stuff. But if you take two polarization filters, one absorbs all of the vertical and one absorbs all of the horizontal, and you put them in front of each other, you get it's just black because none of the light goes through. That's exactly what you would expect. However, if you place a polarization filter that's at a 45-degree angle between those two, right? So you're kind of splitting the difference. One's vertical, one's horizontal, and you're putting one at a 45-degree angle in between them. You'll actually get out some light, right? Which makes no sense from this description, because we're effectively absorbing all of the X and all of the Y. So what's happening? Are we rotating the electric field components? There's no way to describe that though mathematically in here. And so then the next video, we're going to talk about a different way of describing polarization that uses angular momentum to describe it, and the spin of each photon. Just a warning, it's not going to be much more satisfying than this, but I think it's important to tell it to you so that you at least are aware that if you come into a situation where describing polarization in terms of X and Y components of the electric field doesn't make sense with the results that you're seeing physically, you have a thing to fall back